We've talked about the second derivative in the past, f double prime of x. You know, it's just the derivative of the derivative. Now we're going to talk about it in depth. So if you look at these two graphs in front of you, f and g, one of them looks like a right side up bowl, and one of them looks like an upside down bowl. That's how you can basically visualize the difference between these two things. So the first one, f, we say that is concave up. And if you picture any kind of a tangent line to that thing, right, or sketch some in, the curve is always going to be above the tangent lines. So that's another way to look at it. The curve is above its tangents, or again, just if you poured water into this thing, would it stay in it? So G is called concave down. If you picture any tangent line to that, the curve is going to be below the tangent line, or you know, if you would be dumping water out of G, right? If it were a bowl. So we don't use the word convex. It's not concave and convex. Convex means its own thing in mathematics, so it's concave up and concave down. So just visually make sure you get, if I give you a graph, you know which one it is. You should just be able to look at it and tell. Sometimes it can be very subtle, but in general, you should be able to see kind of where it switches. Think about x going from left to right as x increases, as things usually do. What's happening of f, so look at the graph of f, the red one. As x goes from left to right, the function's increasing, but that's not what we're talking about. As x goes from left to right, picture a tangent line going across that thing. The slope of the tangent line is increasing. So, right, if you picture a tangent line moving across that thing, the slopes of it are getting steeper and steeper and steeper and steeper and steeper. Right, so at the very end of it there, the tangent line is steeper than it would be at the beginning. At the beginning, it looks like it's pretty much flat, and then it would just get steeper. Okay, so the slopes of the tangent line are increasing. Well, what is the slope of the tangent line? It's the derivative. That's what the derivative gives you. So for f prime of x is an increasing function, right? F prime is another function. The derivative is some other function. And since the slopes of the tangent lines are getting bigger, that means that f prime is increasing, right? So again, that's not because f is increasing, that's because f is essentially getting steeper, or you can think about it as f is speeding up. If f is speeding up, then the derivative is an increasing function. And what do we know about the derivative of an increasing function, right? The derivative on any interval when a function is increasing, its derivative has to be positive. So the derivative of f prime is called f double prime, and we know that that has to be positive. So the second derivative gives you the concavity. If the second derivative is positive, the function will be concave up. So that's one thing about the graph, really the only thing about the graph, that the second derivative will tell you. So you can see, you can look at a graph and see whether or not f double prime is positive or negative. So f prime being positive or negative makes the function increase or decrease. F double prime being positive or negative means makes the function either concave up or concave down. And it's the same vice versa. So if you look at G and you picture the slopes of those tangent lines, well, they're sloping down in that case. But the important thing is that they're sloping down more. So the slopes of the tangent lines of G as you go from left to right are becoming more negative, right? It kind of starts out, it looks like the slope of the tangent line is 0 on G, and then it looks like it's maybe -1, -2, -3, right? So that means G prime is a decreasing function there, which means that its derivative, G double prime, must be negative. So that's the general rule. So that's all you really have to remember here. If f double prime is positive, you have a graph that's concave up. If f double prime is negative, you have a graph that's concave down. This curve is an important one when you're modeling like population growth. It's called a logistic curve. So if you look at the growth of a species or something, it doesn't just grow exponentially forever. You hit some sort of, you have limited resources. So it grows and grows until the resources start to run out, and then it starts to flatten out. So that's the type of curve you use to model that kind of growth. It's called logistic growth. And if you look at the point, that's an important point. That's the point when the graph switches from being concave up to being concave down. It's subtle, but you should be able to see it, right? Before that point, the graph was concave up, and right at that point, the graph is concave down. That's called an inflection point. And that's a word you've heard before, right? Especially when you talk about something like the spread of a pandemic. At some point you hit what's called an inflection point where the rate starts to slow. So it does have, it is very significant. It's not just a quirk of the graph. So if you picture some tangent lines to this curve, they start off pretty flat, and then they start to go like up, 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 right? They start to get steeper and steeper and steeper. Right when you hit that blue dot, they start to go down again, right? So the tangent line starts here, it goes up. You hit the blue dot, it starts to settle back down because the curve starts to slow down and level off. So the significance there is that's the point when the curve is increasing the fastest. The rate of change has a local max there. So if you were talking about a population, let's say of bees, whatever, you might be interested in the conditions when that happened, right? What was causing that maximum rate of change? If it's a good thing like bees, you want to keep it up. If it's a bad thing like the coronavirus, you want to stop it. So it's actually like a max of the derivative, right? It's a local max of the derivative, and you'd see that on the graph of the derivative of this thing. It would hit a peak. So that's an inflection point means the population or just the function is growing the fastest right there. So you should, right, it can be very subtle, but you should be able to look at a graph and just say, I think an inflection point happens right here, because you will see the switch from concave up to concave down. In this graph, if I didn't tell you, you wouldn't know exactly where it was, but you would have some idea of where it was. So this isn't just math. This is important. The second derivative is important. The third one doesn't really come up in Calc 1. This is a hard thing to do, and this is a thing I'm going to basically make you do on the next test. Now I'm giving you this orange graph, and I'm telling you this is f prime of x. So it is a function, but I'm telling you this is the derivative of some other function. And we're essentially going to work backwards. So that's the thing in math, after you learn to multiply, you learn to divide, right? So unfortunately, at some point in calculus, you have to start doing calculus backwards. That's the next section, though, so don't worry too much about it. Okay, so this is f prime, and I'm going to ask you a bunch of questions about it. For this, you've done this before. F double prime is just the derivative of f prime. So you know how to graph a function's derivative, right? It's not going to be perfect, and I'm not telling you what this function is. I mean, my graph's going to be perfect, but yours could look different and still be right. So you just to look at that max and that min, and you say, okay, f double prime must be 0 there. So in that case, that's right at 1 and negative 1. So you just plot the two zeros. And then you just make a note of the increasingness and decreasingness. So it's increasing up to negative 1, which means f double prime must be positive. It's decreasing between negative 1 and 1, which means f double prime must be negative. And then it's increasing again forever. So it has no choice but to look kind of like a parabola. That is a parabola. But your shape should be parabolic in nature, right? And it should be a right side up parabola. That's really the only possible way it can look. Okay, the purple graph is f double prime. I want to note anywhere that now I want to get information about f of x. This is all about getting all the information about f of x from f prime of x, right? So we're working backwards. It's confusing. So just remember, if the orange graph is negative, f is decreasing. And if the orange graph is positive, f is increasing. So f has to be decreasing all the way up to like negative 1.7, 8, right? And then it has to be increasing from that to 0, decreasing again from 0 to positive 1.78-ish, and then increasing again forever. So we're using the orange graph for that. We're ignoring the purple graph for this step. So right off the bat, you have the basic shape of f. You could actually sketch f right now because you just know, okay, this is a function that goes down, then up, then down, then up. So it's going to be like a W shape, right? So just picture a big curvy W. That's what the basic shape of it has to be. And we get all that just from f prime. Okay, so there's just that in writing. You know, if I'm not giving you like a grid and it's not exact, so if you put 1.7 instead of 1.8, I couldn't exactly mark it wrong. That would not be an exact science. If I told you what this function was, ultimately you would be able to differentiate it backwards and tell me exactly what f was. If you've had some calculus before this, you might already know how to do that. So now concavity, remember we're dealing with the second derivative. So now you can essentially ignore the first derivative. All the information we need about the concavity is going to come from the second derivative. So just look at the purple graph and just say it's positive from negative infinity up to -1, which means f is concave up. It's negative again, it's negative between -1 and 1, which means f has to switch to concave down. And then it's positive forever after x equals 1. So f has to switch back to being concave up forever. So now not only can we graph f, we know what shape f has, we know where its maxes and mins are, and we actually know where its inflection points are too. So we should be able to sketch it with the concavity being accurate. Right, the inflection points are the zeros, notice, of the second derivative. And beyond that, it's not only a zero, but it's where it switches from positive to negative. So it's like the first derivative. If the first derivative switches from negative to positive or vice versa, the function has to hit a max or a min. If the second derivative switches from positive to negative, crosses that x-axis, then it has to switch from concave up to concave down, and that's an inflection point, right? So you know exactly where there's two of them. Okay, so again, this is tricky to do on paper, and your graph may look messy, and it may not look like your neighbor's graph. When you're doing this in real life, it's great to use different colors. I don't know if that really applies to us here. So remember, f has a big W shape. It's going to have... So let's see, go back to the increasing thing. It's going to decrease from negative infinity to -1.8 and then increase again, which means what? It has to hit a min there. So look at the orange graph. It has to hit a min at like -1.8. It has to hit a local max at 0. It has to hit another local min at x equals about 1.8. And then it goes up again forever. So that's that W shape, right? It comes down, hits a min, goes up, hits a little max, goes down, hits another min, and then comes up again forever. And then also, again, this is going to be not quite accurate, but mark the inflection points of it. And try to make your graph reflect that switch. Exaggerate it a little if you have to. Like the switch from concave up to concave down. That's what it has to look like. Basically, let me talk about that a little bit. So we mark the inflection points, right? So the inflection points, this is really what I'm looking for. The inflection points line up with the zeros of f double prime. The two mins and one max line up with the zeros of f prime, right? Just make sure that lines up, and the rest is like, you know, it's going to look how it's going to look. And then just the basic shape of f has to be a certain way. It has to be that kind of right side up W shape because of the positive and negative parts of f prime. So the shifts in concavity, right, they are subtle. And you might, just looking at it, you might not know exactly where they are, but look at them and make sure you get what happens there, right? A thing happens. It switches concavity, and remember that thing has significance because it's a max of the first derivative. So if you look at the first derivative, it has a max and a min. that's where our inflection points are, because that's where the function is either moving the fastest in the positive direction or the fastest in the negative direction in that little local area. And then the other thing is, as far as, well, why did I put f down here? Why didn't I put it up here? Why didn't I put it right in the middle? You don't know that part. The verticality of f is ambiguous. We have no way of knowing. So I could move that graph. Your graph could be like up here, or your graph could be down here and still be right. So that's unknown. Differentiating backwards, there's that little level of ambiguity where you just don't know. Because if we took f and added 5 or subtracted 5 from it or whatever, it would still have the same derivative. So that in particular could look completely different than the person next to you's graph and still be right. We are going to take this function and use our skills finding and analyzing the first and second derivative and just figure every interesting piece of information we can out of it. So the only interesting things that ever happen on a graph are maxes, mins, other critical numbers that aren't maxes or mins, like vertical parts, and inflection points. Other than that, graphs just go about their business. So the function is f of x equals x cubed times e to the negative x. We're going to find any local mins or maxes, basically any critical points, and inflection points as well. And then we're going to compare the graphs of f and f prime and f double prime to make sure everything on there jibes with everything we know about how functions and their derivatives are related. You should be able to just look at it and kind of know what we're looking for, especially like the max. There's only one max there. It's at x equals 3. So that you can tell me right away. You don't even really have to do the math. Now, you do have to do the math, or else I won't give you any credit. But you should know what you're looking for before you dive in, because then you'll know you're right. And then it looks like it hits an asymptote as x goes out to infinity. And then the origin looks like it's not a max or a min, but it looks like a cubic where it just flattens out but then keeps going in the positive direction. So that is, you should kind of see, and there is an x cubed in the function, so that kind of explains it. You should remember that, oh, that's going to be a spot where the derivative actually is 0, and it is, but we can't call it a max or a min, right? We have to be careful because it's not. It's just a flat spot. The inflection points, some of them are going to be a little more subtle, but the origin one isn't, right? The one at the origin is obvious. That's a switch from concave down to concave up. So there's definitely going to be an inflection point at the origin. And then it's hard to say. There's one between 1 and 2 somewhere, right? Somewhere between 1 and 2 it switches to concave down. And then somewhere between 4 and 5 it switches back to concave up. So you should be able to basically tell that. And then we're going to get the second derivative and set it equal to 0 and solve it, and we'll get it, but that's what we'll see. Just dive in. We're doing f prime and we're doing f double prime, so why are you even waiting for me? You should already be doing it. So f prime is the product rule. That's x cubed times negative e to the negative x. Remember the chain rule makes that be a negative come down. And then plus 3x squared times e to the negative x, which I'm going to simplify like that because we have to do stuff with it. In particular, we have to set this equal to 0 and solve it. And right, we want it to be as clean as we can. That's our equation. We've got to be careful. There are no other critical points because this function, this derivative is defined everywhere. E to the negative x can be anything because e to the anything is never 0. And obviously 3x squared and stuff can be anything. So there's no division by 0 possible here. And we don't see any spikes or anything, so we know that's right. So as far as to solve that, just always think factor. Don't think move something to the other side and divide, because then you'll lose solutions. So the way to do it when you have mixed terms, right, we have some polynomial looking stuff and some e to the stuff, is just separate it by factoring. So factor out that e to the negative x, you're left with 3x squared minus x cubed. And then, so right now we'd say, okay, we have to use the principle of zero products. Either 3x squared minus x cubed is 0, or e to the negative x is 0. And here you just kind of have to think. E to the anything can never be 0. In fact, any non-zero number to the anything can never be 0. So think about why that is. We've talked about it. It just cannot be. So that part of the equation is what we would call just extraneous. It doesn't yield any solutions. So just ditch it, right? If a thing times a thing is 0, and one of those things cannot possibly be 0, you just look at the other thing. You literally just erase it and just worry about the other stuff. I've done a couple algebra steps here because you know how to factor. So take out as much as you possibly can, which is in this case is just an x squared. So it factors x squared times 3 minus x equals 0. So obviously x is either 0 or 3. Which is good because that's what we see with our eyes, right? There is a max at 3. And then there's one of those flat spots that's 0. So you don't have to prove that that's not a max. Just use the graph. So don't tell me that's a max when you can see with your eyes that it's not. It's just a 0 of the derivative. If you look at that flat spot, the derivative kind of tells you something about it. So the derivative does touch the x-axis there. We know that because we set it equal to 0 and solved it. So the derivative is 0 there, but notice that it doesn't cross it. It just bounces off. So for there to be like a max there, it would have to switch. The function has to switch from increasing to decreasing, which means the derivative would have to switch from positive to negative, which it doesn't. It does hit 0, but it bounces off because of that like repeated root, because x squared is 0. So it's got that parabola shape at the origin as opposed to a cubic shape at the origin. So that tells you, that confirms that fact that, okay, the function flattens out there but doesn't actually hit a max because the derivative didn't actually cross over. It just bounced off. But then if you look at x equals 3, that's the only spot where the derivative does switch from positive to negative, which means the function actually did switch from increasing to decreasing, which means it hit a max. So the graph of the first derivative will confirm that. And remember that when I say find the local max, I always want to know the other value too. So I always want you to take that number x equals 3 and plug it back into f. And that's just algebra. That's not calc. So just stick 3 in. So it's 3, 3 cubed times e to the negative 3, which is some number. You can simplify that to just 27 over e cubed. So your eyes tell you that the max is at 3. You would need, your calculator could tell you that the max was at 3 comma some decimal, whatever this decimal is. You need to do the math to tell me exactly what that number is. There's just the derivative copied, and then we're going to use that to find, now we're going to deal with f double prime. So just do the derivative again. Now it's more complicated. That usually happens when you start taking derivatives of most functions. It keeps getting more and more complicated as you keep taking derivatives, whatever. So product rule on both of those terms, right? The 3 can stay outside, so it's x squared times negative e to the negative x plus 2x times e to the negative x, and then minus parentheses, don't lose the parentheses there, okay, x cubed times negative e to the negative x plus 3x squared times e to the negative x. So 2 product rules, so now we have 4 terms in this. And we want to clean that up as much as we can because we have to repeat the process. We have to set this equal to 0 and solve it. So don't leave it like that. Get it as nice looking as you can. So I just distributed the 3 and I got rid of the parentheses. This is just like order of operations. Negative 3x squared times e to the negative x plus 6x times e to the negative x plus x cubed times e to the negative x minus 3x squared times e to the negative x. And we're going to do the same thing here we did in the last one when we set it equal to 0. We're going to factor out the e to the negative x because every term has that in common. So I kind of, well, all I did here is I combined 2 terms, so you'll live. So I took the e to the negative x out of every term, and then I rearranged it. So we have an x cubed in there. We have a minus 3x squared and another minus 3x squared, so that means we have a minus 6x squared. So all I really did was combine those 2 like terms, and then we have a plus 6x. In the next move, when we set this equal to 0, again, that e to the negative x is just going to be extraneous because it doesn't yield any solutions. I mean, it's the same process. You just set the first derivative equal to 0 and solve it, set the second derivative equal to 0 and solve it. That factor goes away and you're left with this polynomial equation, which you totally know how to solve. So first just factor out an x. What we're kind of doing when we solve these things is just peeling away factors and then making a note of the solutions that those yield. So right off the bat, you know that x equals 0 is a solution. You can just look at that equation and know, okay, if x is 0, everything's 0. Which means that x equals 0 is an inflection point, which is one of the first things we said. That's the one point where it really obviously switches from concave down to concave up. So just make a note of that and we'll summarize at the end. Now we have to solve this. We have to take the remaining factor and set that equal to 0 and solve it. So you're probably looking at that and going, why doesn't that factor? Well, not everything factors, you know? So you know how to do it anyways. You can either use the quadratic formula or complete the square. To me, this is a primo case for completing the square. That's going to be easy, and I think that's more fun anyways. So that's what I'm going to do. In the interest of time, I just did it all at once. So I'll walk you through it. You move the 6 to the other side, so x squared minus 6x equals negative 6. You take half of that negative 6, right, half of b, and you square it. And you add that to both sides. That's the thing that called completing the square. So you get x squared minus 6x plus 9 equals negative 6 plus 9. So you have to add that to both sides, and then notice that the left-hand side now is a factorable quadratic. In fact, it's one of those perfect square trinomials. So if you've done that right, it'll always factor to x minus 3 squared. And we just have 3 on the other side. Now we can do the extracting square roots things. Just take the square root of both sides. You get x minus 3 equals plus or minus the square root of 3. And then you just add the 3, so you get x equals 3 plus or minus the square root of 3. If you just ignored me and used the quadratic formula, that's what you should have gotten, right? They better both work and give you the same answer. So those are those subtle inflection points that we kind of couldn't tell exactly where they were. 3 plus or minus the square root of 3 is about 1.27 and 4.73. So we did the math, and right, that's something that you couldn't have used your calculator for. It certainly wouldn't tell you inflection points, and it would just give you decimals if it could. So I need to see, when I say exact values, I need to see like something with a square root or something in it to know that you did the algebra. Okay, so we have 3 inflection points, one at 0, one at 1.27. As far as I'm actually not going to ask you really to find the y value, the inflection points. You can just find the x value and then just mark them on the graph. That's what I want to see. I want to see them marked on the graph. So just mark them where they should be. I just used, like, I guess a calculator to say, okay, at 1.27, f is about 0.58, and then over that other one, f is about 0.94. There's no need to take like 3 plus the square root of 3 and stick it back into that original function. You're just going to get some ugly decimal anyways. And again, I don't really care where the y value of an inflection point is. So there they are marked. The blue ones are the inflection points. And now you can see when you look at it, like, oh yeah, it does switch there. Especially with that second one, it's extremely subtle, but you can see it. You can see it switch from concave down to concave up. And then the blue graph is f double prime. So notice that the blue graph crosses 3 times. It crosses the x-axis 3 times, and that gives us our 3 inflection points because it does cross. It switches first from negative to positive, which means the function switches from concave down to concave up. That's the obvious one at the origin. And then the other two, it just switches again, right? It's only going to switch one way or the other, although a function can hit an inflection point and then keep being concave up, but most don't, so don't worry about that. Okay, so f is the red graph. That's the one we were interested in analyzing. F prime is the orange graph. That gave us our max and then our flat spot. And f double prime is the blue graph. So I wouldn't expect you just to glance at a function and know what the graph of f double prime had to look like. But I could make you do it by just getting F prime and then getting F double prime and then graphing them like as accurately as you can. So the concavity of the thing, it's just, look at the red graph now, concave down on all the way up to 0. We usually start abbreviating, so you can go ahead and abbreviate CU and CD. I'll know what you're talking about. So it's CU up to that first inflection point, concave down up to that second inflection point, and then it looks like it's concave up again forever, and it is. If it weren't, we would have gotten some more inflection points, so you know it is.